All right, welcome, ladies and gentlemen, back to Chapter 5. We are going to be diving deep into our proofs, or basically simplifications. Really, all these proofs are is simplifying one side to make the other side look the same. All right, so we're going to use all of our fundamental trig identities to prove complex trig identities. Now, you have identities that are on your paper that are proven for us, and we're going to be using those to prove other identities. Kind of like we did in geometry. You were given a set of postulates and theorems, and then you could use those postulates and theorems to prove other theorems. All right, so let's take a look. There's a lot of what this looks like before we actually get to the examples. So first of all, the proof is going to begin with one side of the identity. You are not allowed to work across the equal sign. So things like this, where you go 3x plus 1 equals 0. You're not allowed to subtract 1 from both sides. So obviously we're not going to do something simple like this. You have to be able to simplify one side to make it look like the other. So the proof starts with one side of the identity, so one side of the equal sign. Whenever I say one side, that means across the equal sign there. And the proof ends with the other side. So you have to make the left look like the right, or the right look like the left. The proof in between consists of showing a sequence of baby steps of equivalence, which basically means you're writing down something that's the same. So if I started with cosine squared x, I could rewrite, let's say this is equal to blah, 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 blah. I could say, oh, well, I know cosine squared x could be written as 1 minus sine squared x equals blah, 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 blah. I haven't changed the right side at all. I'm writing down these. This would be a baby step of equivalence because these two statements are the same thing. I could then even go like this. This is 1 plus sine x times 1 minus sine x. Maybe that would be helpful for us in the future for this particular problem that has no answer. Okay, these statements are the same. All right, so these would be my baby steps of equivalence. All right, so the next page is going to look a little bit daunting, but this is the general strategies of what to do. All right, so first of all, work with only one side of the identity at a time. So you're not allowed to add to both sides. You're not allowed to cross multiply, so don't even think about it. You may work with both sides, but it must be done separately. So you can simplify the left and simplify the right separately to see if they come out to the same simplification, and that's a legal process, but you're not allowed to do anything to both sides of the equal sign at the same time. Big thing is cross multiplication. Cross multiplication is illegal math. All right, begin with the more complicated expression because those are the easier ones to simplify. It's easier to simplify something complicated. It's rather than trying to take something that's simplified and make it more complicated. That's a very challenging process. One of the kind of little strategies here is if you can't think of something to do, change everything to sines and cosines. So if you're given tangent of x, change it to tan of x, change it to sine x over cosine x. It creates fractions, but it creates things that might end up canceling later on. Or if you're given cosecant x, change it to 1 over sine x. One of the things that you're going to show up here is you're going to end up having fractions that you need to combine. Well, that means you need common denominators. So you're going to need to be multiplying trig functions together, getting sine squared, cosine squared, all that sort of fun stuff squared. A plus b times a minus b to set up a Pythagorean identity is super, super nice because if I was to give you 1 plus sine x, if I was to multiply this by 1 minus sine x, I would get 1 minus sine squared x, which is cosine squared x. So that's nice and easy. A lot of the times this ends up in a denominator where you need to simplify a fraction. This actually is pretty nice because it creates If this was your denominator as a sum, this creates a single piece in the denominator. And so it will actually help you in the long run. Just make sure you pay attention to all fraction rules. Be mindful of what the target is. Where are you expecting to go? So if you start with tangent and your final product should have sines only, you don't want to change everything on one side of the equal sign into cosines, because that's not what I want. Now you'll hear me say this a few times when we go through when I work with you. I'm usually thinking 3 steps ahead, because I don't want to write something down that's not really going to help me. So I always kind of think, well, if I did this, what's it going to give me 3 steps down the road? But here's the thing. In preparing for this lesson, I did a problem, and I had to do it 4 or 5 times because I couldn't figure out where I needed to go. Eventually, I got it, which brings me to this one. Always try something. I didn't just give up on the problem and change the problem for your benefit. I kept trying stuff until I got it so I could show you how that particular problem works. All right? So one of my kind of pet peeves in this lesson is when people come to me and they say, how do I do this problem? Well, I can look at your paper, and if you didn't write anything down, if you didn't try the problem, that means you didn't even look at step 7 here. You have to try something. This is a problem-solving type of section, and you need to be able to think for yourself rather than get me to tell you what the first step is always. You need to be able to figure out a first step that could lead to a second step that could lead to a third step. But if you never try anything, that means you're not even paying attention to any of these statements that I'm telling you. So always try something. If anything comes back to you, go back to, if nothing comes to you, just try something. Number 7, okay? You have all of these little strategies here. Now I have 3 examples for us in this particular video. I'll try to get more videos up on different examples from the textbook as well. So here's our first one. This is what an identity proof is going to look like. So we want to show that these 2 statements are equal. Well, I can't add or subtract to both sides of the equal sign, so I want to look at one side of the equal sign by itself. So I think the left side looks more complicated, lots more fractions. The right side looks kind of simplified. So I'm going to take the left-hand side and I am going to make it look like the right side. So what I look at here is I notice that I have 2 fractions. And on the right-hand side, I don't have a sum of 2 things. I have a product, which means I probably should combine these fractions. So I need common denominators. Well, it's super nice the fact that these 2 things are conjugates of one another because things are going to come out really nice here. So on the left side, now remember we're dealing with just the left side of the equal sign here. On the left fraction, I need to multiply by secant x plus 1 and secant x plus 1. And on the right side, I need to multiply by secant x minus 1 and secant x minus 1. Well, let's see what this gets. Multiply the numerator, that's super easy. Secant x plus 1 over, multiplying conjugates together, that means the in your FOIL, that means the O and the I goes away. So secant times secant is secant squared. And plus 1 and minus 1 make a minus 1. Plus, kind of the same thing over here on the right fraction. I'm going to combine my numerator. I'm not going to deal with my denominator just yet. If this was me doing the work, I probably would do 2 steps at once, but I want to make sure you guys see where I'm going here. Secant x plus secant x is 2 secant x. Well, that's good, actually, because notice I have a 2, and that's actually what I want here. I have a 2 at the final product, so It's looking promising. All right, so secant x, well, I have a +1 plus -1. That makes 0. That's nice. Well, now where should I go? Oops, sorry, secant squared -1. So the question is, where do I go now? Well, whenever you see, now this isn't always the case, but a lot of the times this is the case, whenever you see a quadratic trig function, you should think Pythagorean identity. And it just so happens that secant squared x minus 1 is equal to tangent squared x. Okay, so coming over here, I'm going to say, okay, this is actually 2 secant x over tangent squared x. Well, this still doesn't look like my piece here that I want. Well, but I do have a cotangent, and I have a tangent now. Well, notice that we're being divided by tangent, so this is actually 2 cotangent squared secant x. Well, here's a problem. This it still doesn't look like the thing that I want. It's getting closer, I think. I have a 2 and a cotangent, but I have a squared cotangent and a secant. So let's try some more stuff. I don't know where to go, so let's go and change everything to cosines and sines. So cosine squared x over sine squared x times 1 over cosine x. Well, I'm going to have to come up here because I'm going to run out of room. Notice this, I can do some canceling here. I can get rid of one of those cosines and that cosine and be left with 2 cosine x over sine squared x. Well, it kind of looks like I went farther away from the answer, but because this fraction can actually be split up into cosine x over sine x times 1 over sine x, notice this thing is still the same as this thing. These are kind of some of the little tricky things that you need to know how to do with fractions. One of the things that I always stress is using fractions, and now you're going to be paying for it if you've never figured out your fractions. All right, so notice that cosine over sine is cotangent, and 1 over sine is cosecant. Holy cow, we got what we wanted. We have now just proved this identity. Okay, so notice we kind of combined fractions, we did some simplifying, used our basic identities, and got down to the final answer. All right, what about the next one here? Cosine x over 1 minus sine equals 1 plus sine over cosine x. So you have to resist the urge to cross multiply. Don't do it. Now, in this particular case, you could work with either side. You could work with the left side first or the right side first, and not even first. You could use either one, but I think the left one, I like it a little bit more just because the more complex thing is in the denominator. So it looks more complex to me. So I'm going to deal with this one. I'm going to deal with cosine x over 1 minus sine x, and I'm going to use my Pythagorean identity. Remember one of the things I said, use a plus b times a minus b to set up the Pythagorean identity. So I'm going to multiply by 1 plus sine x. And as long as I do it to top and bottom, it's all legal. So I get, in the numerator, I get cosine x times 1 plus sine x. I'm not going to bother multiplying yet because sometimes I don't do that. I mentioned this in the last video because sometimes things will cancel before I need to actually distribute. If I multiply the denominator together here, I get 1 minus sine squared x. Well, the reason we did this, by the way, was to get a Pythagorean relation or Pythagorean identity. And 1 minus sine squared is cosine squared. And you'll see now why I didn't multiply here, because this cancels with one of those. and I'm left with 1 plus sine x over cosine x, check mark, done. So notice how simple that one was. Really nice and quick and easy. I'm not even pretty sure. I know the same process would have worked for the right-hand side if you would have multiplied by 1 minus sine x over 1 minus sine of x. It would have came out the same thing, and you would have gotten this as your answer. All right, next one here. Last one for this particular lesson, if it would work for me. There we go. This is the challenging one. This is the one that took me a little bit of time. This one, the reason it took me a little bit of time is because I couldn't see it. And that happens every once in a while. I can't always see everything here. But what we're going to do here is we're going to actually, because I already know where we're going, we're actually going to work with both sides separately. So I want to simplify the left and simplify the right separately here. And what I'm going to do is I'm going to look at this cotangent squared, and because it's a quadratic, I'm going to look at my Pythagorean identity, and I know that cotangent squared is cosecant squared minus 1. Now, there's a reason I did this, because cosecant squared minus 1 actually factors to cosecant x plus 1 and cosecant x minus 1. And if you look here, I have a cosecant x plus 1 and a cosecant x plus 1, which means the left side of this equal sign simplifies to this. Now, the reason I knew to work with both sides of the equal sign is because this statement now looks very simple. And it looks like it would be hard to write it as this statement. So because this is simple now, I'm going to go back and I'm going to start working with the right side of the equal sign. Now I have something multiplied by a difference, but I can't see how that would help me. I do see what ends up being cotangent times tangent, and since they're reciprocals, that's going to be 1. So let's see what this is going to look like. I don't know where to go, so let's change everything to sines and cosines. So cosine x over sine x times 1 over cosine x minus sine x over cosine x. If I was to distribute this, cosine over sine times 1 over cosine, my cosines cancel, and I'm left with 1 over sine x minus, I already told you this is 1 because they're reciprocals of one another. Well, oh, this looks super nice. So I have minus 1, but 1 over sine of x is actually cosecant x minus 1. And because you've simplified both down to the same answer, check mark and done. Now, there technically is a way to write this as one full proof from one side, make it look like the right side. But for the most part, if you just simplify the left and simplify the right separately and come down to the same answer, that means you've proved the statement. All right, so here's an assignment. We have a two-part assignment. Notice I give you a ton of problems, 4 through 57 all. And then those 4 extra ones at the end. Some of them are fast, some of them take a while. I think what I give you here, 11 different problems to do that are actually due to me in 2 different parts. I would suggest doing more than just those 11. All right, this is a very difficult concept. It's a very difficult process, one that takes practice probably more than any other ones that you've ever done before. So good luck. I will see you guys in class. Have a good evening.